Hello, hello, Mr. Corey. Can you hear me? Okay. So let's progress forward. So these are testimonials. Okay. So let me quickly read through the seven objective for Precision Agriculture Incubation Program. So the seven objective behind the Precision Agriculture Incubation Program. Number one is to close the knowledge and the skill gap for participants about precision agriculture technologies and practices. Number two is to raise the next gen agricultural remote pilots. To number three is to groom young precision agriculture leaders and stakeholders for global exploit. Number four is to build the capacity of youth in the aspect of technology application in agriculture. Number five is to promote the adoption of innovative and sustainable farming technologies that improve agricultural productivity and resources management. Number six is to foster entrepreneurship and encourage participants to develop technology driven solutions for agricultural challenges. And lastly, number seven is to create a network of digitally empowered young agricultural professionals who can drive positive change in the agricultural industry. So this program falls into two categories. Okay. So this program falls into two categories, which is the entrepreneurship track and the employability track. The entrepreneurship track empowers individuals to launch their venture, providing the knowledge and the resources necessary for establishing successful and social business enterprise. And the employability track caters for you to have the employable, employable skill set that makes you to be competitive in your industry, emphasizing employability in agriculture technology and research roles. Also, we have the focus area. The focus area is on drone technology, GIS and data, GIS data and remote sensing. Uh, Also, robotics and Internet of Things, and lastly, enterprise development. Okay, so now let me bring to the stage the organizer of the program, Precision Field Academy. So the Precision Field Academy, at Precision Field Academy, we have a vision to create a world where every young person, regardless of their background, has the opportunity to become a digitally savvy farmer or agricultural professional, driving sustainable and equitable growth in their communities through the transformative power of technology. And our mission is to raise next gen farmers that are tech inclined and digitally savvy. So, about Precision Field Academy, we are a social enterprise. We train and build the capacity of young professionals in modern and emerging technologies for the future of work and to lead with precision agriculture. So, our methodologies are majorly three: education and knowledge sharing, training and skill development, coaching and mentorship. And we have major tech skill in focus, which are basically six: drone technology, geographic information technology and remote sensing. And that's the course we have this morning is based on satellite imagery, and so it's classified under geographic information system and remote sensing. We also have as a tech skill data science for agriculture. We have robotics and internet of things, artificial intelligence and machine learning, enterprise development. So why do we do what we do? Our motivation: there is a skill gap that need to be closed, and young professionals need to build those skills on both technical and enterprise skills for the future of work in agriculture. Number two, we note that observing the trends is not just enough. So youth need to be an enabler. They need to be involved directly. They need to be a player in the fourth agricultural revolution and not just mere observers. And lastly, technology is the key to unlock African agriculture potential. So why should you join us? We are creating a future we want in agriculture. We also connect you to the world of information and opportunities in terms of scholarship, internship, volunteership programs on both local and international scale for your career growth. Also, we have skill development through project collaboration, community interactions, and workshops. And lastly is access to coaching and mentorship from industry leaders and professionals. So at Precision Feed Academy, we are building a community of young tech inclined and digital service professionals. All right, thank you. So I'm going to be reading the profile of our speaker this morning before I bring him to the stage. So our speaker for today is Mr. Corey is an art data scientist at Amini in Kenya. So, and he's going to be speaking to us on the topic satellite and remote sensing technology in agriculture this morning. So, let me quickly read through his profile. Uh, okay. Mr. Corey is a geospatial data scientist at Amini, a cutting-edge environmental data infrastructure tech company in Kenya. Corey stands at the forefront of geospatial technology in agriculture, pioneering innovative solutions through product design and development, leveraging remote sensing and data science methodologies. He crafts tailored made solutions for agricultural sector, ranging from crop type classification to crop yield prediction and crop health monitoring. Driven by a profound mission, Corey is committed to empowering smallholder farmers and aiding their resilience to climate change by delivering data-driven insights that promotes regenerative agriculture practices beyond agriculture. The data processed by Corey's team finds utility across various sectors such as crop insurance, farmers financial inclusion, and digital extension services. So Corey's mantra is data is the current era new oil, encapsulates the transformative potential of data in shaping the future of agriculture and beyond. He firmly believes that by harnessing the power of data, optimization of resources within the agricultural landscape, it will drive improved outcomes for farmers and communities. Okay, Mr. Corey, you have the floor now. I just did a slight introduction about you. So if you can hear me,
Thanks a lot, Joseph, for
okay.
that beautiful introduction. I Can you hear me well?
You can share your slide from your
You
hand
can
if
hear
you
me
have your
well. You can hear me all
slide on.
right.
Come again, sir.
Can you hear me well?
Yes, 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 yes. I can hear you.
Oh, okay, okay. So I think we can get started, right? Okay, okay. So I think we can get started. Let me try and see.
You can go ahead, sir. You can go ahead, sir. So you can share your screen.
I'm able to see my screen, right?
Yes, yes, yes. I can see your screen. I can see your screen.
Yeah. So today, just a minute. Yeah, so today we're going to talk about remote sensing and GIS and the intersection of remote sensing and machine learning and data science. So we're going to talk about a lot of things, but majorly we're just going to talk about data in agriculture. I know in the recent past that data has not like had a lot of traction when it comes to agriculture, and most farmers were just like heavily dependent on the conventional methods of managing their farms using the traditional methods, uh, and not so much effort or energy had been directed towards agriculture when it comes to issues to do with data and technology. So today we just want to do a dissection or a postmortem of the of the state of remote sensing data, data science and AI in agriculture. So what does it mean when you talk about using remote sensing in agriculture? What strikes your mind when you hear about remote sensing in agriculture? Remote sensing as for quite a number of times be used in management of natural resources, talking about forests, talking about doing what is called change detection, how forests changed over time, so and probably monitoring water bodies and all that. But now comes into an era where we are now starting to use remote sensing in agriculture. So to just start off, I just want to probably just jog your minds a bit. Whatever you're seeing in your screen right now, that is a farm. That is a plot. It's a plot. It's a farm somewhere in Kenya. You can be able to see it. These are two farms. So I was able to plot something for two farms. So when you see these, you just see a graph. This is just data that comes from the farm. What does it mean? What information does it hold, and how can it help us? How can it help farmers? At the end of the day, you as a farmer, how can you leverage into this technology? So maybe even before I go far, I think I'll just start from talking about remote sensing and just trying to explain what a remote sensing is all about, right? Just trying to explain what remote sensing is all about. So let me just share this tab instead. No worries about the warning there. So according to what is called USGS, we are told that remote sensing is a process of detecting and monitoring physical characteristics of an area by measuring its reflected and emitted radiations at a distance. So this is a non-intrusive method of collecting data. So take for example, I have my remote control here. And when I want to watch my TV, I always ask, where is the remote control? Why? Because I don't want to get into contact with the television. I just want to use my remote so that I can be able to now to change the channels or do whatever I want to do on my TV set. So that is remote because there is no contact. It is a non-intrusive way of controlling things. So, and when it comes to remote sensing, it's still the same thing. Take for example, when you're taking a picture, when you're taking a selfie, just take your phone, then you take a selfie of yourself, right? Or when you're taking somebody else has told you, would you take a photo of me? So you take your camera or you take your phone, then take them a photo. When you're taking this photo of them, it's non-intrusive. You're just clicking somewhere, then you get a picture. So there is some physics behind it. There is some physics behind it, and there is what is called about light traveling from the object back towards the camera. So that is the simplest form of remote sensing, because you're trying to get information from an object without having contact with it. And what enables this to happen? So in physics, maybe some of you read about this, or you learned about this probably in your it depends, in your grade, whichever grade it was. You can see here in the screen there's something called the electromagnetic spectrum. So this is a range of channels, or I can say bands or frequencies, where we have different frequencies. For example, we talk about microwave, infrared, visible. Visible is the one that you can be able to see with your own eyes. Visible. Then we have ultraviolet, X-ray, and gamma rays. So when you're taking your photo, what happens is there's light that comes from the object that comes into your phone, and that is what is recorded in the visible area of the electromagnetic spectrum. So that is what enables cameras to be able to capture information. And they'll capture information in the visible part of the electromagnetic spectrum. Here we're talking about your phones only, or maybe the cameras that you always use. So electromagnetic spectrum is the one that helps, to capture this information non-intrusively. So now when it comes to remote sensing, I think you're cognizant of the fact that we have satellites that are orbiting the Earth. And they're taking, pictures of the Earth at intervals, but at the end of the day, they'll have, the whole picture of the whole Earth, after some time. So they take these images at different intervals, right? And they'll come back to the same place after a certain time. So these satellites take imagery or take images. So when these satellites are orbiting the Earth, they have what is called a payload or a sensor which has been attached to these satellites. So these payloads or sensors are the ones that are taking the photos, the normal photos that we take. But now in this case, I'd shown you about the electromagnetic spectrum, and I said for the normal cameras, it's just whatever you're able to see or whatever the camera is able to capture is just from the visible part of the electromagnetic spectrum. But now when it comes, and that is called the RGB, that is red, green, and blue. But now when it comes to the satellites can be able now to capture information from different parts of the electromagnetic spectrum, including the visible part. And it's called multispectral. This other one is called RGB. For satellite imagery, most of them always capture what is called multispectral imagery. Why? Because they're able to capture information from a variety of channels in the electromagnetic spectrum. So when they're moving and they're capturing information, they're able now to capture information from these different channels of the electromagnetic spectrum, and that is what makes them a bit unique. Yeah, I'll be able to explain to you in a bit why it does make them unique. So, and when they're doing that, now we have two different types. We have two different types of sensors. We have what is called the optical sensors, and we have the microwave sensors. So when you look at the optical sensors, these are they're able to measure the ultraviolet, visible, and infrared wavelengths. But for microwave sensors use the microwave, part of the electromagnetic spectrum. So what is the difference between optical and microwave? For optical, they're always affected. They're always affected by whatever is in the atmosphere. We're talking about clouds. We're talking about hygroscopic materials in the atmosphere, or anything, dust. We have so many things in the atmosphere. So for optical sensors, because they're passive, we talk about passive, it's just from the reflected light and can only be done during the day. Now, that is the reason why it's being affected. But for the microwave sensors, from the microwave portion or the microwave part, it has a very special characteristic that it can be able to penetrate. It can be able to penetrate through these hygroscopic materials and clouds and whatever it is in the atmosphere, and it can be able even to penetrate, the vegetation on the surface of the earth, and be able to capture in information from there. So, so that is all about introduction to to remote sensing. Just wanted to talk about that. Yes. So, so what do we have next? So I talked about different characteristics of satellite imagery, because when these satellite imagery or when these satellites are moving around. Yes, Joseph, I can't hear you. I can't hear you. Just a minute. I can't hear you at all. Are you muted? Hmm. Okay, I think I can continue, right? Can't hear you at all. Just a minute. Let me rejoin. Let me leave, then rejoin. Can you try something? Oh, this is weird. Yes. Would you write it in the chat box? I can't hear you at all. I don't know where the problem is. Can you hear me? Can you hear me, right? Okay, okay. I was talking about the optical sensors and the radar sensors, or the microwave sensors, and the difference between the two sensors. And that is how we are able to get our information from the satellites when they are orbiting the Earth. Okay, thank you for that. So we're talking about three characteristics of satellite imagery or satellite image collection. This is just a starter for remote sensing. Maybe there are people who, you know, understand much about remote sensing, others do not. Maybe just to give you a little bit of, sneak preview of what remote sensing is all about. So, talking about satellite image collection and their characteristics. So, the first one that we have is called the spectral resolution. So, when you talk about the spectral resolution, you remember when here we talked about the electromagnetic spectrum, and we say that we have different wavelengths, and we have the cameras that we have, or the satellites that we have that have sensors. They're able to capture information from different wavelengths. So when we talk about these wavelengths have names. We have the red band, we have the blue band, the green band, we have the near infrared, we have the shortwave infrared. Those are what we call bands. And when you're talking about spectral resolution is now how many bands, how many channels, how many wavelengths can these sensors capture information from? So that is what is called the spectral resolution. The more the channels, the better. I'll be able to tell you why. The more the channels that the satellite imagery can capture, the better, because we have more information from a single image. Now, what about temporal resolution? So temporal resolution is all about when the satellite is going round, orbiting the Earth, it will capture an image of this specific area where I am at the moment here in Nairobi, and it will orbit again the Earth, then comes back and takes a picture of the same place where I am. So that is what is called temporal resolution. How long does it take for the satellite imagery to image the same place? We have different satellite constellations in the atmosphere. Maybe we have Sentinel, we have Landsat. Those are where those are the ones that we get data freely. For example, for Sentinel, the revisit time is like, I think, 6 to 7 days. We have Landsat, which is around 16 days. So that is what is called the temporal resolution, how fast. So, and now this also determines the use case, because the more the frequency, then it can be used for something. And we have other use cases that does not even need a higher temporal resolution. So what about spatial resolution? Sorry. What about spatial resolution? Spatial resolution is it's about how discernible an object is, how clear an object is. When you're taking images with your phone, we've talked about pixels, right? Megapixels or something of the sort. I don't know, 50 megapixels. They're trying to tell you how clear the photos that you take with your camera in your phone are. So the same applies to satellite imagery. We have what is called spatial resolution. So when you talk about spatial resolution of 10 meters, it simply tells you that the spatial resolution of 10 meters, an object which is less than 10 by 10 meters cannot be easily identifiable by the satellite imagery. But an object which is more than 10 by 10, a dimension of 10 by 10, for example, a house, it can be easily identified by the, not a house, maybe a dam or something, or a farm which is 2 acres and above. It can be easily identified by the satellite imagery. So that is what is called the spatial resolution. So we've talked about spectral resolution, talked about temporal resolution, and now the spatial resolution. You remember what I was telling you? At a spatial resolution of 1 meter, the image is clearer. At 10 meters, we start seeing, it fading away, and that is how it goes at 30 meters and 250 meters. So maybe this is an example, 10 meters is an example of a Sentinel-2 optical image. There's a Landsat image and all that, right? Yeah. So let me also introduce you now to another very important concept, the concept of vegetation indices. So in the whole agricultural spectrum, when we talk about things to do with crop monitoring, when we talk about things to do with detection of water stress in crops, detection of areas that have been burnt in crops, we are trying to apply, machine learning models in agriculture, just trying to do things like yield prediction. Most of the times, the things or the data sets that are being used are called vegetation indices. So vegetation indices, in short, these are just, let me now take you back here. Vegetation indices, remember we talked about the different types of wavelengths. And I remember telling you about red, green, blue, near infrared, shortwave infrared. These are numerical values. These are pixels in the satellite imagery, and they hold numerical values. So when you talk about vegetation indices, we are talking about mathematics. We are just looking at the ratios between the different channels that we have. So here we're talking about red and near infrared. That is one vegetation index. So there is a way in which we do. Maybe we say, so the vegetation indices, we have so many vegetation indices, and these ones are always, always derived depending on the characteristics of vegetation. Depending on the characteristics of vegetation. So when you see the reflectance that comes back from the surface of the earth, or let's say from the vegetation, there is a way in which, in all those bands, in a multispectral imagery, there is a way in which the plants or the vegetation reflect each and every band. They reflect each and every band in a different way. We have the red, the red band. Maybe it absorbs. In the red band, it absorbs light. In the near infrared, it reflects when the vegetation is healthy. When the vegetation is not healthy, maybe it's the reverse, or maybe the values are lower. So that is what is called vegetation indices. They're just trying to do some ratios between the different bands to just try and characterize the vegetation, to tell us what is happening in the vegetation. So when we combine vegetation indices and domain knowledge, this is now where value comes in. This is now where the insights comes in. So as it is, satellite data is just data. We have not appended any kind of insights into the satellite, into the data. But now when you start having these vegetation indices, and merging it with domain knowledge, and merging it with plant characteristics, now that is where the insights come in, and that is where the value starts coming in. So for example, we talk about one vegetation index that we derive from satellite imagery. Satellite imagery, let me repeat again, is a layer of different bands. When we talk about multispectral is a layer of different bands from the electromagnetic spectrum. Let's say red, green, and blue. So those are three bands that are layered together, and each band has different numerical value depending on the characteristics of the surface of the earth. Let's start with the first one, normalized difference vegetation index. So this is the most widely used VI, and it measures the difference between the near infrared and the red bands of the electromagnetic spectrum. I presume that you've heard about NDVI maps, even for drones. When they're taking pictures, they always take pictures. For drones, they always do. They're multispectral, but they take data from 4 wavelengths: the red, the green, the blue, and the near infrared. So from the near infrared and the red, we do band mathematics. The band mathematics will give you NDVI, and this one now will help you explain what is happening in your farm, because the NDVI is all about greenness of the vegetation. how green is your vegetation? How green is your vegetation? So we have enhanced vegetation index, which is an improvement of normalized difference vegetation index, that is NDVI or NDVI map. So we have soil adjusted vegetation index. Now for the soil adjusted vegetation index, this always applies, in arid and semi-arid areas, or when the plant is just, when the crops are just starting to grow. They're just trying to account for the soil, reflectance and all that. So that is the reason. That is the reason why we have soil adjusted vegetation index. Then we have normalized difference moisture index. Crops are growing. You've put it under irrigation, and you do not have enough water, or we are experiencing drought. How are you able to determine whether your crops are performing well or not? Comes in your savior in normalized difference vegetation, normalized difference moisture index, because it kind of tried to explain to you the moisture levels in your crops, because it looks at the leaves. Is it wilting? Is it getting enough water? Yeah, so those some of the indices. We also have normalized difference water index. This is used to monitor water bodies, because there is a way in which water bodies, they there is a way in which they reflect the shortwave infrared and the near infrared and the other bands. So using that, now we are able to create these indices. I believe up to there we are good. Now, when you talk about we've talked about vegetation indices, right? And probably just have thrown in probably and or given hints on how it can be able to be used in the whole agriculture spectrum. Now comes in what is called time series analysis. Now you've planted your crops, right? You've planted your crops. And of course, when you plant your crops, you would need to monitor your crops from the time that you plant your crops up to the time that you harvest your crops. And remember, when you talked about the characteristics of satellite imagery, we talked about the temporal resolution, talking about how frequent does this satellite take the picture of the same place. So now that explains what is called the time series analysis, because once we have frequent data capture for a specific place, it will now enable us to be in a position to monitor your crops, over time. So, when you plant your crops, we're able to monitor the vegetation index. Of course, I'm just taking this as an example. You've planted your maize, right? So we will monitor your crops when you plant and monitor the NDVI value. We'll be having probably the NDVI value always values between maybe 0 or -1 to 1. So we are monitoring that value from the time that you plant your crops up to the time that you harvest your crops. And that is the basis onto which crop monitoring is done. Yes, so I just want to talk about. I think I've talked about just the basics of remote sensing, but today we just wanted to see the application of remote sensing in agriculture. But before we talk about that, probably I'll just talk about just a minute. Just a minute. Sorry for that. Yeah. So we just have a few challenges of using remote sensing in agriculture. So I'll be able to explain to you later about the challenges. Maybe let me just talk about remote sensing in agriculture and how it helps. So let's talk about okay. So let's talk about the first one here, which is very crucial. In agriculture, we have so many things. We have so many things that affect crop growth. First, we have drought. We have insufficient nutrients in the soil. We have pests. We have diseases. We have floods. You know, we have crop lodging. We have rainfall. Rainfall. If you have less rainfall or high rainfall, that leads to flooding and all that. But now comes the remote sensing, and remote sensing is just a tool that will help in identifying some of these factors that affect crop growth. And of course, we're talking about crop monitoring challenges. But again, this satellite imagery that we are talking about does not just help in crop monitoring, it also helps in other wider aspects of farmers' lives, including farmers' financial inclusion. How can we use remote sensing to be able to enable farmers obtain loan products? How can we help farmers using remote sensing to be able to reform and go into regenerative agriculture practices? How can you also use remote sensing to bring affordable insurance? And the word is affordable insurance, whichever insurance you're talking about, whether weather-based or index-based or indemnity-based insurance. How can we make that possible for farmers? So remote sensing has really played up to the moment a very big part in trying to address some of these challenges that we are facing in the agricultural spectrum. So we talk about crop yield prediction, and crop yield prediction helps in what we just talked about in financial inclusion and ag insurance. How? So when you talk about yields, yields are very key because yields can be used by financial institutions to understand your farm profile, to understand, you know what, this person this year, the yields that we are projecting for this person is this much, or the yields of this person for the last 5 years has been, 2 tons per hectare. And we want to advance loans to farmers. You as a financial institution, how can you do that? Because for a very long time, farmers have lacked a chance, and we talk about smallholder farmers mostly, they do not have, most of them do not have, a better percentage do not have collateral. But they have land. They have land that they've been tilling for quite some time. Can we use that land and be able to extract information from that land and be able to use the information that we get from that land to enable farmers be included in the financial, realms? So remote sensing can help in this. Agriculture insurance. Agriculture insurance, you've heard about index-based insurance and weather-based insurance and all that. So when it comes to index-based insurance, for example, when we are grouping farmers, in groups or in insurance units, then we are compensating them in case there is a calamity that has struck them. And we are using yield to determine that. If the yield has gone below a certain level, then we say that the farmers have been affected by the said has been affected by the said calamity. So how does it happen? It happens because we are doing crop yield prediction, and the crop yield prediction, I know we have the conventional methods or the crop models that we use, but now it comes in remote sensing that can be able to quantify what has been happening in the farm. And in that aspect, we're able to understand the changes in the crop yield, even things to do with basis risk in insurance. Remote sensing has come in very, very handy in trying to, alleviate these issues. So, remote sensing helps in crop yield prediction. I think I've explained that even in the insurance world, creating those thresholds and getting funding or loans for their farming activities. Another thing about agriculture again is about crop type mapping. That is the total area under production. How can we do this? Let me just show you a picture. Let me just show you something. That just a minute. Let me stop. present. Let me share screen. Window, entire screen. Just a minute. These. Okay. Are you able to see my screen? Yeah, so I just wanted to show you this is what is called a crop mask. This is a crop mask of a certain area in Kenya. It's called Uasin Gishu County. You can be able to see Uasin Gishu County has quite a number of crops being grown in the long rain season. The long rain season starts in April or March, April, and May. And mostly the crops that are grown in that area are wheat and maize. Maize taking, I think, around 70% of the total crop area at this particular moment. So what I've been able to do here, or what I've been able to do here is I've been able to create what is called a crop mask. This is a crop mask of maize. Whatever you're seeing here, whatever you're seeing in black here, that is maize. Maybe somebody can ask, why is it that I'm seeing some parts here which does not have anything? And those are wheat farms. Those are wheat farms or farms of other things. So this is what is called a crop mask. And a crop mask, typically, how we are getting this data. Remember, it has been very hard to plan, or it can be very hard to plan for a local government or for a national government when it comes to food security, or statistical officers, country statistical offices. I mean, they will just want to understand, or create what is called a regional food balance sheet. As a local government, or as a county, as we call it here in Kenya, as a county, how much maize have we grown? How much area is under production? And when we take these data, does it mean that we are food secure? Can we create a full balance sheet to say that, what, we have this amount of crop under production? And when you have this amount of crop under production, and the average yields around this place is this, then we are expecting production of this much, right? Do we have that? So before this, I believe that we've been using, statistical processes like doing sampling, then extrapolating the data. But voila, here we are. I mean, we are having technology that can be able to tell you which crop grows in a certain area, So it helps policymakers, understand what is happening on the ground when it comes to issues to do with agriculture. So this is one of the things that has been made possible by use of remote sensing. So let me stop the screen and go to another one. Let me share screen again. Worries about that. Yeah, I'm able to see my screen again here. Just a minute. sorry about that. So earlier we had talked about this graph you're seeing here. So this graph is an NDVI graph. It's a normal difference vegetation index. You remember we talked about vegetation indices. So this is a vegetation index. So I've taken the near infrared and I've taken the red bands of this small area. Let me see that area. Just a minute. I just want to show you. Yeah, this small area. This is a farm. This is a farm, and we just want to understand this farm from the time that it was harvested up to the time that it was, for the time that it was planted up to the time that it was harvested. Then we have another farm here. So we have two farms. The other one is plot 1, this is plot 2. So as you can be able to see from these, this is plot 1 and this is plot 2. So what does it mean? These stats are from January 1st. From January 1st, here you go. So planting is always done around planting is always done at around towards April. As you can see here, it's almost April. You can see the graph starting to grow, right, or to go up. These are the NDVI values. Remember I said when the vegetation is very low or we have no vegetation, the NDVI value is a value between -1 and 1. So when we do not have any vegetation in a farm, the values tend to be very low, maybe close to 0. But when the vegetation is very healthy, you see that as we're headed towards this time, we're talking about October here. We're talking about from September to October. This is the time that we are having the highest value in the NDVI. Why? Because we have a lot of vegetation. The vegetation is healthy, probably, and it has not started tasseling or flowering. So that is why you're seeing it here. So it starts down here. Sorry. It goes up, it goes up, it goes up to here. Then it goes down again because around here, maybe here, there was some harvesting that was done. Again, it goes like that down up to again April the next year. Now this is 2024. It now starts again going up. And we are in October. And you've seen that most farms have dried up. Some of them have been harvested. That is for the first farm. For the second farm, it's also exhibiting the same characteristics because it's from the same area. Planting around April, maturing around let's say August, same thing around August, and going down because it has started drying. So that is how we are doing crop monitoring. So of course, we have a baseline. We have a baseline to say, you know what, when it reaches a certain crop stage, so we have different crop stages. When we start here, it is VE, that is there is emergence of vegetation. Then we have V2, V4. We talk about V2, V4. We're talking about the leaves. You're talking about maize in this case because these are maize farms. So when you're going to VE, you're going to V2, V8, VT. VT is when the plant is starting to tassel. Then we start R. R is the reproductive stage. V is the vegetative state. So when you start R, that is the time that now the cobs start forming. So at different stages we have baselines, and we have we have baseline data. That tells you, at this particular time, this is what it's supposed to be at this particular area. So that is how we are doing crop monitoring. And of course, also when you're looking at these, let me share this. When you're looking at this farm, maybe there are pests and diseases that are devoured this farm. Maybe this area. How are we able to see this? I wish I could have done for this, but you'll be able to see because the NDVI values in this area will be having color codes and we'll be having green, and we'll be having probably towards brown areas that probably are exhibiting brown or yellow. That those are the areas that probably are not doing well. So telling the farmer, hey, Would you go to the middle part of your farm? There is something happening in the middle part of your farm. Maybe it's pests that have devoured that part of the farm. Maybe there was an issue with fertilization, maybe the nutrients in that area, or maybe it's a slopy part, or maybe the farm starts being slopy at that part, so the nutrients gets leached towards the lower part of the farm. So those are some of the insights that we share, with farmers when it comes to crop monitoring. So these are some of the things. That we do, or we're able to use remote sensing in agriculture for. So share again something, just a bit. Yeah. So we've talked about crop type mapping. We've talked about crop monitoring, digital extension services, and yeah. So we've heard about digital extension services and crop monitoring. Satellite image or remote sensing has played a very big part in doing digital extension services. So it's no longer just sending out blanket messages, or generalized messages telling the farmer, you know what, when it reaches this time when your farm is almost flowering, please do this. No, right now we are journeying. It's a voyage with the farmer. It's a journey with the farmer from the time that you plant, monitoring the farm, what is happening in your farm. There's something happening in your farm, the weather is not good, so the farmer is on toes. The farmer and you both are on toes, because you are alerting the farmer as time goes on by. And these with the proliferation of mobile, phones and all that, SMSs and WhatsApp and IVRs and USSD, farmers are in a position to get this data just on their mobile phones. Yeah, so that is where we are with crop monitoring. So now I just want to talk about the challenges that we are facing in agriculture. So the first one is when you talk about crop type mapping, when you talk about crop yield prediction, your getting yield data is not an easy task. It's not a trivial task. Getting yield data. Yield data is gotten through a process called crop cut experiments. Like, it's a 3-step process depending on the crop. So getting that data is very, very hard, and this kind of slows down the process of modeling in the agriculture space. And crop type mapping, here we're just talking about crop boundary data or polygon data, georeference data. So there's something that I always say that for crop or for remote sensing in agriculture to be able to get value, it starts with the polygon, one polygon at a time. It starts with the polygon. Getting into the farm and getting the polygon of that farm, that is the genesis of the transformation of agriculture. That is where the transformation of agriculture starts from, that polygon. Very important, because the moment I get that polygon, as an analyst, as a data scientist, I'll be able to churn out insights or create analysis of that farm, near real time, sending that data. So that is where it starts from. So availability of ground truth data is one of appearance. You remember we talked about optical sensors. Those are the clearer data that we get. And if we have a lot of clouds, or you have areas that have a lot of clouds over the year, so it will be very hard to be able to get data unless we use the microwave sensors. We have spatial resolution. There are some things, or there are some services or things that we'd like to do with remote sensing, but spatial resolution plays a very big part. Why? Because if we cannot be able to monitor intercrop systems, or we cannot be able to distinguish intercrop systems. Why? Because the data that we use mostly are like 10 meters resolution, And for 10 meters resolution, it will be very hard for you to discriminate between whatever have been the intercrops. It will be very hard for you to differentiate that. And also, we also see that we have smallholder farmers whose farms are very small. So if we have satellite imagery that are not satellite imagery whose spatial resolution is high, is low, then it will be very hard to be able to get information for these smallholder farmers. So spatial resolution plays a very good plays a very big role, in carrying out some of these tasks. So what about the last one? I think not the last one. Talking about data availability and accessibility. Um, Data availability. But I can say that of late, when talking about satellite data, we've been having platforms, different platforms that are now offering, cloud computing platforms that are now offering platforms where one can be able to analyze data, big data, quickly, efficiently. Cloud computing platforms. It was very hard. It was very hard uh, to because you had to download data into your machine. Now, your machine maybe doesn't have enough RAM, doesn't have enough storage. It takes a lot of time. You have to do what is called cloud masking or remove clouds from the imagery, and maybe you needed time series data. So imagine how we have a lot of computing platforms. Yeah, but it's still an issue. It's still an issue. That is being currently worked on by different organizations, like Amini. Amini has created um, a, a, a satellite computing platform where people can be able to access data. Can be able to access. It's called they can be able to access data efficiently. And even time series data. They can be able to get time series data in a CSV or an API format. So yeah, so that is one of the issues also. Then we have interpretation and integration. Yeah, so we have data, yes, but have we created enough platforms that can interpret this data well? Do you have enough people or scientists who are in a position to interpret this data and transform it into actionable insights? Because data without domain knowledge cannot do anything. So we need data, somebody who can analyze this data, somebody who can merge the domain knowledge experts and be able to merge this data to be able to give power to this data as insights or information. Yeah, so those are some of the issues that we are facing in the agriculture sector when it comes to remote sensing. Yeah, so up there, I think it's question time, right? Yes. Are there questions? I think I saw some questions, but I don't know how I can be able to access them. Joseph? Actually can't hear you. Again? Maybe it's your earphones. I can't hear you.
Okay. Hello.
Yeah, I can hear you now.
Okay, good. Thank you. So it's really insightful to learn about the potentials of satellite imagery in precision agriculture. Uh, we talked about yield index, crop classification, crop mapping, crop health monitoring, and all of those factors. Yeah, I think it's really a good one, seeing the potential of what satellite technology can be used.
You froze. Hmm. Let me see. I think I've seen some questions in LinkedIn. Uh, why is the graph suddenly dipped on July? There's a sudden dip on maybe August. Uh, Maybe an issue with these would be the dips can either be issues to do with data preparation. Maybe cloud masking did not mask all the clouds or mask all the bad pixels well. That is why you're seeing a dip. But the dip can also be an indication of something having happened in the farm. A very steep dip, you know, that could be an issue with the data quality. But a small dip could be an issue with maybe there's something that happened in the farm. So those are some of the key things that we look at when you're looking at interpreting this data. What could have caused some of these dips? Yeah. Sorry. Please, could you show me briefly the process from data collected by satellite or drone to ML and the results? Yes, maybe not now. Maybe you can send a request. Then I'll be able to show you. But yes, collect the data. As I said earlier, you have farms. You have farms. When you have these farms, are you able now to collect these vegetation indices or the data itself or the bands itself? When you collect them now, and you have, let's say you're doing crop yield prediction and you have the yields of those farms. So when you have the yields of those farms, then you collect these numeric data, talking about NDVI data from the time that you plant or at a certain point during the crop growth cycle. You take all this data, then you use this data now to create a model, maybe a crop yield prediction model. So yeah.
Hello, Mr.
Yeah.
Corey. Sorry, I had a network glitch from my end, so I am currently back. So this was one of the questions. This is one of the questions we had earlier while the class was going on. So
Okay. Greetings. I am Gideon Afolabi. You're welcome. The category of indices is hyperspectral imaging. So when you talk about hyperspectral imagery, I remember we started with RGB. RGB is red, green, and blue. Then we went to multispectral. Multispectral is these are imagery that have that captures data from a variety of bands. Let's say 10 to 15 bands. When you see Sentinel-2, it captures from around 12 or 16 bands. Here we're talking about the usual RGB, which is the visible, then the others like shortwave infrared, and we have near infrared and others. So those are multispectral. Multispectral are countable. But when you go to hyperspectral, this means now that the sensor is capturing information from a lot of wavelengths, including all the wavelengths that are in RGB, multispectral, and others like the gamma rays and whatever. I think these are sensors that are always used, maybe in radioactivity or something of the sort, in X-rays and all that. So hyperspectral, a lot of wavelengths. Multispectral, accountable. RGB just 3. Yeah. So that is how hyperspectral imaging works.
okay, thank you very much, sir, for giving that answer. Okay, I want to quickly search for more questions we have here, so we can bring them on board. Inside this. Oh. Hello, Mr. Corey. Hello. Okay. These are another questions here. Ah,
Sorry. I was
all
muted.
right.
Yeah, I think Deborah just asked about successful cases of remote sensing in agriculture, considering the limitations. Yes, we have the limitations in remote sensing in agriculture, but we try to mitigate these limitations. So we have so many successful cases. We view remote sensing data in weather-based index insurance. We've used remote sensing in doing yield prediction, in doing what is called crop type detection. We've used them in all these cases. So yeah, we have a lot of cases. So when you talk about crop yield prediction, crop type mapping, and talk about crop monitoring, these now just opens the door for so many other things to be done. I think I earlier mentioned about ag insurance. I talked about farmers' financial inclusion. I talked about crop monitoring. I talked about digital extension services. So these basic things that I've just talked about opens up, opens up the door to so many other use cases. Yeah.
Okay. Thank you very much. I'm trying to get other questions. If you have any other question. All right. Basically, this is not a question. The person is just giving an heads up, a comment. It was such an educated section, sir. Thanks so much. Uh,
You're welcome, Gideon. Thanks, Deborah. You can always reach out to me via by Precision Field Academy or via my LinkedIn profile. Yeah.
Okay, thank you very much, sir. I think we don't really have much questions now. We have some questions from LinkedIn previously, and when uh, we had a network glitch, we lost those questions. Okay, so we've finally come to the end of the presentation for this section, satellite and remote sensing technology in agriculture. We're able to show us some software platforms, I think Google Heads, Google Engine, and how you can use them to gather data around precision agriculture. So I just want you okay. So I just want you to give like a word of encouragement to our participants, or viewers, before you leave this morning. If you can hear me, so
Yeah. So thanks a lot. When I started out focusing on matters to do with remote sensing and data in agriculture, I didn't see it as something that I would take on for quite some time, but it's something that I've grown to love. I've faced a lot of challenges along the way, but this is a sector, or this is a sector that is growing and is gaining a lot of traction. Reason: the population is increasing. The population is increasing, and the demand for food will continue being there. So what are we doing? You know, what are we doing as a youth? What are we doing as farmers? What are we doing as analysts? And all those other, all the other skills that people have. What are we doing to make sure that with the resources that we have, because the resources that we have will continue being the same, or some of it will diminish. So with the resources that we have, how can you maximize on it? How can you maximize on it to make sure that we improve, we increase yields, we're able to produce more food, right? So it presents an opportunity to so many people. The first opportunity that probably I always give out there is data, data collection in agriculture. People are still not collecting a lot of data or action or useful data in agriculture. We need to collect more data in agriculture if we want to steer this sector in the right direction. We need to collect a lot of data. Collect a lot of data. We need to involve experts, in agronomy, experts in agriculture. We need to involve experts in things to do with data science, in geosciences, and all that, and in soil science and all that. So it's a sector that can can invite a lot of professionals into it, whatever you do. So you don't have to be a farmer, you can be an analyst, dedicate your skills into agriculture. Yeah. So what I can just say, just find a niche in agriculture, work on it, look for partners, look for stakeholders, look for players in the agriculture sector, try to understand their pain points, trying to understand what is it that they're trying to do, but they can't get it right. And that is where you're gonna get your answers. That is where you're gonna get what you want to do, and that is how you're going to carve a niche in the agriculture sector. So I'm encouraging people who are in different fields, um, even fields that probably you never knew that could be applicable in the agriculture sector. And I'm telling you, come, there is a space for everyone in the agriculture spectrum. There is a space for everyone in the agriculture realm. So you're welcome. Let's make sure that we turn this agriculture sector into something that is worth it. Yeah. Thank you.
all right. Thank you so much, Mr. Corey, and thanks for sharing your honest opinion and word of advice for participants. I believe this will really help them to also see clearly better and change their mindset, yeah, towards embracing Christian agricultural technology. It's really nice having you here, sir. So much to learn, so much you have shared with us this morning, and we are sincerely grateful for you honoring our invitation. So it's such an awesome class. Thank you so much, sir.
You're
Uh,
welcome.
and we believe that in the near future, if we call on you, yeah, you will be willing to also share with us.
You're welcome. You're so much welcome, and thank you also for affording me this
All right,
chance.
thank you so much, sir. The entire on behalf of the Precision Field Academy team, we want to say a very big thank you for coming. All right.
Okay, bye.
Okay, we've come to the end of the. See you next time, sir. Bye.
Bye.